start. So this is a part of the European American Collaboration Wind Energy online seminar series, where we this is second Wednesday in the month have a seminar with either Americans or Europeans, or it could also be from anywhere else. But it's just to have some collaboration, some exchange of ideas in wind energy research. And today's speaker is Jim Brasseur, who's professor of aerospace engineering sciences at University of Colorado. He has been a mechanical engineer professor for several decades at Pennsylvania State University, where he works with turbulence simulation, LES, and so on, related to atmospheric physics, but he's also done a lot of work in medical fluid mechanics, so fluids inside you swashing around.
Gastrointestinal tract.
Yeah, gastrointestinal tract. And now he's going to talk about non-steady forcing of wind turbine main bearing by passage of atmospheric surface layer turbulence eddies. So please, Jim.
Okay, thank you very much. Yeah, this is the original title. They shortened it when they made the flyer. Very good, thank you. So I wanted to first acknowledge that most of the work that I'm presenting today came from the PhD thesis of Jared Kenworthy, who's on the phone, and there's his photograph. And this was in collaboration with a group at the University of Strathclyde. Jared was part of that group. Ed Hart is also second advisor, and John Keller. All right, my advance isn't working. Okay, there we go. All right, so there's John and there's Ed. Okay, yeah. All right, so the work has to do with the way in which atmospheric turbulence, in particular the atmospheric surface layer, which is where the wind turbines reside, interacts with the wind turbine, particularly the rotor, and creates time-varying loads on the blades, and the blades then integrate to provide time-varying loads at the hub, which then transfer down the drivetrain, the main shaft, and interact with the components on the main shaft. And in particular, I'm going to focus on the main bearing for this talk. The upper left-hand photograph, let's see, a movie. Let's see if I can put the laser pointer on, okay? So this movie on the left-hand side is a large-eddy simulation of the atmospheric boundary layer in the daytime. It's at 90 meters, which is the hub height for the NREL 5 megawatt wind turbine, which is the wind turbine that we use in these simulations. And what it's showing is horizontal fluctuating velocity, the velocity relative to the mean, which is around 10, 11 meters per second in this particular simulation. Okay, the fluctuations vary pretty large from the mean, several meters per second, plus or minus several meters per second. So that's plus or minus 10 to 50% of the mean velocity. And what is showing in the blue is the low speed streaks that are ubiquitous in the surface layer of high Reynolds number turbulent boundary layers. And even though this is a moderately convective boundary layer, the high speed regions are shown as well. They're not as organized as the low speed regions, but these regions, lower and higher speed than the mean flow, pass over the wind turbine. I'm showing the size of the NREL 5 megawatt wind turbine. It's 126 meter diameter wind turbine. And as it passes over the rotor, it creates time-varying forces on the blades, which then integrate to time-varying loads at the hub, which is this point right here. So I'm showing the drivetrain in the right-hand picture. The forces that are or the loads that are generated at the hub are moments. Oh, I see. I'm sorry, things got started a little bit messed up, so I'm therefore still a little bit messed up. But at any rate, the moments and the forces act at the hub, and then these pass down the main shaft. The main bearing is sitting right here, and they create loads on the main bearing. And in particular, if one does an equilibrium force balance on the main shaft, you can produce this equation for the force that is acting directly on the main bearing. That's this force F bearing right here, and the main bearing right here. And this force on the right-hand side, I've written it where I've taken the contribution from the weight of the rotor, which is sitting right here, and I took it to the left-hand side. So all the terms on the right-hand side are the aerodynamic forcing terms, and these are associated with the out-of-plane bending moment or the radial bending moment at the hub. That's this MH perpendicular. This is a modified version of MH perpendicular. And then the radial force that's acting at the hub, this FH perpendicular right here. So these two aerodynamically controlled terms then create the aerodynamic contribution to the main bearing force, which is right here. So we're very interested in what generates the time variations in these two terms right here, and then how that generates the time variations in this force vector that's acting on the main bearing. The force vector that's acting on the main bearing is important for the function of the main bearing. The main bearing consists of two series of rollers that are passing through the load zone. The load zone is generated by this force that is acting on the main bearing, by the main shaft. And so that would sort of illustrated by these red rollers right here. And the load zone then gets moved around both in terms of the magnitude and the direction. It gets larger and smaller in magnitude, but it also changes its direction. And those changes in the magnitude and the direction of the force interact with the rollers and interact with the bearing itself. And presumably we argue at any rate that these are probably the primary mechanisms associated with the failures of the main bearing. And main bearings are failing too soon. They typically are failing within 8 to 10 years when a wind farm is supposed to last 20 to 30 years. So this is a main issue. This is a primary issue for wind farm developers. I wanted to point out that this picture here is related to the equation, which is the radial moment vector and the radial force vector, which are on the right-hand side. And the radial moment vectors is this one right here. It's the out-of-plane moment vector. It's the non-torque moment. It's the moment that generates motion on the main shaft due to the tilting of the rotor plane itself. But of course, there are other components. The axial component to the moment is the torque, and that's what generates the power. And that's, of course, of interest as well. And the axial force that is acting at the hub gets passed directly to the main bearing. And that is of interest as well, because that force then can also distort the main bearing along with the radial force that is acting on the main bearing. But all of these forces are being forced or being changed by the passage of these eddies through the rotor plane, interacting with the blades and with the rotor as a whole. And that's what the focus of today's talk is on those interactions and how that generates the moments and the forces of the hub, which then get passed to the main bearing. All right, one of the previous results that was published in this work down here that actually goes back to the time that I was at Penn State, and my former students at Penn State generated this result, which has been redone by Jared in this plot right here. And it's basically the result is showing that the out-of-plane bending moment, the one that is in that equation that I showed you, this component right here, is uncorrelated from the axial component to the moment, which is the torque. So that is to say that the component that generates power, the torque, is uncorrelated with the component that generates the forces on the main bearing. They're from two different mechanisms. And of course, the main bearing failures go into the operating cost. So that's in the numerator of the levelized cost of energy. Whereas the axial moment, the torque goes into the power, which is the denominator, the energy production of the levelized cost of energy. So this is basically saying that the numerator and the denominator of the levelized cost of energy come from different mechanisms. We do know from the previous work that the torque itself, which is the power, is driven by the average wind speed over the rotor plane, the horizontal wind speed over the rotor plane. That's a very, very high correlation coefficient. That's close to 1. and so on, and the thrust as well. All of these are very highly correlated, but they're uncorrelated with the out of plane bending moments, the one that generate this force on the main bearing. And we're particularly interested in the time variations in the force. So in order to study the details of these interactions between the low speed and high speed streak regions and the wind turbine, and the generation of these moments and forces that then interact with the main bearing, we did a series of computer simulations. These are high fidelity computer simulations using large eddy simulation, very well resolved large eddy simulation with a state-of-the-art actuator line model to represent the blades of the NREL 5 megawatt wind turbine. So I'm showing on the left-hand side, the domain is 5 kilometers by 5 kilometers by a couple kilometers in height. I'll show that in a second. And that has to resolve the eddy structure, the energy containing eddy structure of the atmospheric boundary layer, in particular the surface layer. But I want to point out that this is a daytime atmospheric boundary layer. It's a canonical daytime atmospheric boundary layer. It's one that's been studied quite a lot. I've studied it quite a lot. So a lot is understood about, you know, the dynamics and the structure of this boundary layer. But one of the important issues is that there's vertical velocity fluctuations generated along with horizontal fluctuations. And these will cause the fluctuating velocity vector to bend up and down, as well as grow larger and smaller in magnitude in the horizontal direction, which is what this picture is showing with the streaks and so on. So in order to resolve this flow field and also resolve the blades of the wind turbine, modeling just the rotor part of the wind turbine itself, we use the AMR wind code from the National Renewable Energy Lab, which has built into it adaptive mesh refinement, AMR, adaptive mesh refinement. And we use the adaptive mesh refinement to refine the grid around the blades and around the rotor. And this is just an illustration showing how it's done with 3 different levels of refinement down to the blade level, going up to the atmospheric boundary layer level. The blades themselves are represented using an actuator line model, high accuracy actuator line, sort of state-of-the-art actuator line model that's built into the AMR wind code and contains also the filtered lifting line correction model that was presented in this paper by Tony Martinez and Charles Manabeau in 2019. And Tony was at NREL, and we worked with him in implementing the filtered lifting line correction. It increases the accuracy, but it also reduces the cost of the simulation, which are both very important. The basic idea is to represent the blade with a series of actuator points. We represent the blades with about 150 actuator points. And these actuator points then are representing the forces at each point on the blade, which use table lookups to get from the CLC alpha curves and so on. And then the forces at each of these actuator points is spread over a spherical volume, which is represented by this expression right here, and then is passed over onto the grid of the computer simulation for the velocity field itself. So I won't say anything more about it, but it's state-of-the-art. The only higher quality representation would be a full blade boundary layer result simulation, which Ganesh Vijay Kumar, a former student of mine, has done in the past and is still doing, but they're extremely difficult, expensive experiments to do. And these capture the time. We've already shown that these capture the time transients very well, so it works very well. So this shows the basic parameters for the simulation. The domain itself is about 5 kilometers by 5 kilometers by just under 2 kilometers. The capping inversion is this number right here. That's the height of the boundary layer. It's about 1 kilometer. The grid resolution is about 10 meters in the horizontal, 15 meters in the vertical. The surface heat flux is set to be consistent with the daytime boundary layer and the geostrophic wind.
Sunshine.
Yeah.
All right, somebody please mute yourself if you would.
You both move down to the other. Thank you everyone joining us.
David Shannon, would you please mute yourself? Thank you. All right, geostrophic wind is 15 meters per second. That's the wind in the mesoscale, just above the capping inversion. So these are typical for the daytime boundary layer. And the capping inversion height, like I said, which is the boundary layer height, is about 1 kilometer. This is the stability parameter, the global stability parameter for the atmospheric boundary layer. It's negative for the unstable daytime boundary layer, and the magnitude is about 4.4, which is typical. 4 to 6 to 8 is sort of typical in the daytime. Actually, 2 to 8 is typical in the daytime, depending on time of the day and time of the year, etc. And the mean velocity at hub height, which is 90 meters, is about 12 meters per second. The blades themselves are resolved down to 0.5 meters. Typical chord is 2 to 4 meters for this wind turbine. I said 150. There's 300 actuator points along the blade, and we're using the filter lifting line correction. These are all parameters associated with that. When you do the simulation, of course, there's long transient periods, and you wait for the simulation to go into a stationary state period, which would be this time period right here. This shows the time period of the simulation from the beginning until we reach the stationary state, which took quite some time to do. But we select about 1,200 seconds, 2 minutes in this quasi-stationary period for doing our analysis. All right, so this is sort of the first results slide, as it were, and it's really kind of important. I'll spend a little bit of time on this slide. So what I'm showing on the right-hand side is the horizontal plane. The red are the fluctuating horizontal velocities, positive above the mean, and the blue are negative below the mean. And I'd like to point out that the range is really very large, plus or minus, say, 6 meters per second, shown on this picture, and the mean velocity is 12 meters per second. So that's quite a major variation. And as these high speed and low speed regions pass over the wind turbine, this is the wind turbine right here, and this blue region here is the wake of the wind turbine, which is being simulated using the actuator line approach. But as these higher speed and lower speed regions pass over the wind turbine and the blades which are cutting through, of course, they're changing the characteristics of the response. And that's one of the primary issues. That's going to be at the time scale of the advection of these large structures, these coherent energy-containing structures past the wind turbine rotor plane. So this is the wind turbine rotor plate. Here we're looking at it straight on in the transverse plane, and it's showing the blades rotating, and it's also showing the isocontours, again, of the horizontal fluctuating velocity, which are fluctuating, in this case, mostly in the blue, that is low speed region is passing through at this particular time. And you can see that there's very large gradients in the rotor plane, and the blade is cutting through these gradients. And as the blade cuts through these gradients, of course, it's experiencing a response at the time scale of the blade passing through one of these concentrated regions of high gradient. And that's going to lead to a response in the forces on the blades, which integrate to response in the moment and the force at the hub, which then gets passed over to the main bearing as a force acting directly on the main bearing. So the point right away that you can see is that these time variations are going to be large, because the variations in the velocity are large, and that they are going to be varying with time, and they're going to be varying over multiple time scales with time, and that's going to be a focus of what I'm going to say as we move on here. All right, so one of the issues then is this force. So the right-hand side of the force that's acting at the hub of the main bearing, this point right here, is the radial force. That's this FH perpendicular vector, but there's an axial force as well that gets passed over to the main bearing. So one of the things the main bearing manufacturers are interested in is how the axial force may be distorting the main bearing. So there's some interest in understanding the relative magnitude of the axial component of the force to the radial component. And that's shown here. The blue curve here is the axial component of the force that is acting. Actually, this is the force on the bearing itself, but the x component of the force on the bearing is the same as the axial force, which is acting at the hub itself. And the main point is that the contribution from the radial force is much larger than the axial force on average, but that there are these periods where the axial force is actually larger. They're highly time dependent, and they're dependent on the turbulence generated variations in time. This is an issue that needs to be looked at. We haven't really focused on this, we've focused our attention on the radial force and the corresponding radial contribution to the force that's acting on the main bearing. But I bring this up as something that we should look at, and we will look at as time goes on. All right, so let's start off with sort of a pictorial understanding of the frequency content of the signal. So I'm showing the signal here. This is over a 200-second period in order to be able to see the time variations clearly. The top is the torque. The middle is the bending moment at the hub, the out of plane or radial bending moment at the hub, and the bottom is the bearing force magnitude. And I already pointed out from previous work that the torque and the out of plane bending moment are uncorrelated with each other, whereas the bending moment at the hub and the force are highly correlated. In fact, as I will show you, it's totally the bending force at the hub totally generates the force at the main bearing itself. So these are correlated at the 0.9 something level. Right, so one of the key observations to make here is already the torque is uncorrelated from bending moment, that the bending moment is correlated with the force acting on the main bearing. But the other point is to note that the variability, if you kind of look at these numbers on the side, they're comparable. The variability around the trends, this green line is the trend line, and I'll come back to that in a minute. But the variability around the trend line is much larger for the hub bending moment, the out of plane, the non-torque bending moment, than it is for the torque itself. And that's important because what it means is the mean of the hub bending moment is somewhat less than that for torque. But because the variability is so high, there are actual times when the magnitude of the hub bending moment, the out of plane bending moment, is actually larger than the torque, but typically they're of order the torque. So that means that the aerodynamic loads that are generating these moments at the hub get split between the torque, the part that generates power, and the out of plane bending moment, the part that is impacting the main bearing and influencing the operation of the main bearing itself. It gets split between those two components. Comparable, they're of the same order, and that's important because it means that the aerodynamic forcing is contributing both to power and to failure mechanisms at the same time. Another point to make before we go, I'm going to tend to focus on the magnitude of these vectors. These are vectors, however, so that the vector that is acting on the main bearing is changing in magnitude as well as direction. So I'm showing a polar plot here where the magnitude is given by the radius on this polar plot. So as the vector of the force acting on the main bearing changes, it's moving in this direction. But its magnitude, its orientation is shown by this direction here. So the angle of the vector itself is being shown here. And the point to make is that the variability in direction is really large. It's not just a variability in the force itself, but the direction of the force is also changing as well. We have analyzed the direction, and it's very important, and it correlates somewhat with the force, but in a complicated way. But the main point is that there is huge variability in both the direction and the magnitude of the force that is acting on the main bearing in response to these aerodynamic loadings at the hub. Another point is that the variability is around a mean that is shifted due to the weight of the rotor itself, which creates a constant moment around or a constant force contribution to the main bearing, and that's shown with the black dot, which is modulated by the mean shear. The mean shear actually generates a contribution that tends to lift it tends to be vertical on the main bearing, whereas the weight goes the other direction. So they counter each other. But the point, I guess, is that the variability in the magnitude as well as the direction, but the magnitude varies from very large values to very small values, almost zero. It's pretty impressive, actually, how much variability there is in this vector. All right, now let's get into the time variations themselves. So if you look in detail at these three plots, the first thing you notice, of course, is the 3P variation. The 3P variation is the response due to the blades passing through the internal gradients within the velocity field on the rotor disc itself. And these gradients come from multiple sources that I'll talk about in a minute. But this is a geometric response in the sense that there's 3 blades that pass through continuously. So there's going to be a response at the rotation frequency of the blades divided by 3, because there's 3 blades, and that's 1.65 seconds. So it's somewhere between 1 and 2 seconds. And these are very well-defined responses that appear in all the signals associated with the rotor disc. So this is sort of the orientation time scale itself. But there are larger and smaller time scales as well. And of course, all these time scales are being passed down the drivetrain and impacting the main bearing. So that's why these are important to look at. The larger time scale are these, you can see them. I've identified 40-second period here, and there's a 90-second sort of variation here, and you can see them. They're roughly between 10 and 90 seconds if you look at this carefully. And that's due to the passage of these coherent eddies. These coherent eddies, these low-speed, high-speed streak regions are passing through. And if you examine the length, the size of these eddies and their characteristic mean velocity, this is the kind of timescales you get. So these larger timescale variations, these trend variations, as it were, are due to the passage of these coherent groups of eddies through the rotor disc. So that's lower frequency than the 3P frequency, or larger timescales than the 3P timescales. But there are shorter timescales as well. And you can see these, I've identified a number of these with these circles, but you can see it happens all over the place, that you get these much higher frequency responses as well. And we'll go into this in some detail, but these higher frequency responses are a result of the blades passing through those individual high concentration, high gradient regions that are changing with time as the eddies pass through the rotor plane. And as the blade passes through them, they generate a response, and they generate a response to the time scale of the blade passing through those coherent regions, which have a smaller length scale than the rotor disc itself. And it generates a very broad band of higher frequency content. I'll show you that in the frequency plot in just a second. But the point is then that there's these 3 different ranges of timescales: the 3P timescales, the larger than 3P timescales, and the smaller than 3P timescales. So if we go back to the equation for the aerodynamic contribution to the force acting on the main bearing, there are 2 terms on the right-hand side, and these 2 terms both have these timescales in it. So the first question, of course, the one asked, is the relative contribution of the out-of-plane bending moment term on the right-hand side and the radial force term at the hub on the right-hand side. And it turns out that the force contribution of the hub is negligible, and I'm showing that with schematic, or with this particular plot, which is over a 40-second period, but this is on average the case. In fact, these are the statistics as well. The force term is on order, a couple orders of magnitude smaller than the moment term, and this just shows that that's true. The green dot is the force term, and the moment term is the blue, and that's much larger. This is the term to the force equation. This is this term right here. So that it's much larger, and it's varying all over the map, like I showed you in the earlier slide. But it's also strongly correlated with the force that's acting on the main bearing. The radial force on the main bearing is the red, and they're basically tracking each other. There's a small difference between the two, because this term is not 0, but it's very small. So really, the moment term is everything. The time variations in this moment term, the out-of-plane moment term, dictates the time variations in this aerodynamic contribution to the force. The weight contribution is a constant, and that just represents a shift in this blob, as it were, on this in this transverse plane. But the variations are totally due to these terms on the right-hand side. All right, now, so 3P is obviously the organizational time scale. It's about 1.65 seconds. And to show where this 3P comes from and how it's impacted by the turbulence, we did 2 simulations. One simulation is without turbulence, but it has the mean velocity profile for the LES, large eddy simulation that we did, but no turbulence. And this is the response that one gets. This is the moment at the hub due to the mean velocity profile, the blades passing through this gradient, the mean velocity profile, but not the turbulence. And you get this 3P response. It's very well defined, it's extremely periodic, but it also doesn't change its magnitude in time. So this is a pure 3P response. On the other hand, if you add turbulence to this, then you get this signal right here. This is the same time period, 200-second, a 100-second time period, I guess I'm showing here. And it's showing that the 3P is still very obvious, but it's totally distorted. It's modulated the envelope of the signal hugely, and it's created this larger timescale variation that I called the trends earlier, but it's dramatically altered the structure of the 3P signal. And this alteration of the structure really comes from two sources. Here I'm showing the spectra. The first is the spectrum associated with this, with the precursor calculation over this time period right here. And then the red is the full turbulence simulation over the 1,000-second time period. And there's a number of things that you can observe. First is that in the pure mean shear calculation, there's a single spike. That's at the 3P frequency, and pretty much the frequencies are pretty much negligible, or the energy content is pretty much negligible at all other frequencies. But when you add the turbulence in, it does a number of things. One of the things it does, it takes this 3P signal and it spreads it out over a range of scales that are a result of the turbulence interacting with the 3P signal and spreading the 3P signal out over a range around the 3P peak here. So that's this kind of triangular range of frequencies right here. The second thing it does, and really importantly, is it changes the magnitude. You can see in this picture here that there's about an order of magnitude difference between the peak in the blue and the peak in the red signal. And if you look at these two signals, you can see it here as well. This is plus or minus 200 kilonewton meters, and this is about 2,000. So the turbulence has two dramatic effects on the 3P signal. One is it modulates the 3P signal a lot, and the second is it changes its magnitude a lot. And that's because the blades are now cutting through many gradients within the rotor plane, not just the mean gradient, but it's passing through all the gradients associated with the turbulence, the internal structure of these turbulence eddies that are passing through the rotor plane, and the blades cut through this over and over and over again, and add more and more variability, or more and more variance to the variability, and increases. So this is important because these are all going to get passed down the drivetrain and interact with the main bearing. Yeah, so this is sort of an important result that impacts the fluctuations of the main bearing. But in addition to increasing the 3P fluctuations a lot and changing it and modulating their form, it also creates these lower frequencies. Basically, the lower frequencies didn't exist before, and now they do. And it creates these higher frequencies, which didn't exist before, and that now they do. So recognizing that there's three different frequency bands, the 3P frequency, the lower than 3P, and the higher than 3P, we want to examine these separately. I should also point out that these additional peaks are the what's the
higher harmonics?
Harmonics. My brain just froze for a second. The harmonics of the 3P. So they're all related to 3P, the 6P, and so on. So anyway, so recognizing that there's three different frequency bands, and so obviously of interest to analyze the content of these three different frequency bands and their contribution to the force that's acting on the main bearing. So we now do a series of analyses based on filtering the signal around the 3P band, which is this red region right here. So we take this triangular region and we filter here. We didn't want to include any of their harmonics, so we filtered just up to this point. And then the higher frequencies, we chose not to include the first harmonic, but we are including the other ones, which aren't so dramatic. So higher frequency band is this one here, goes up to something like 40 hertz. We cut off here because this is sort of a noise floor thing going on here. And then the low frequencies are low pass filtered to capture the low frequencies. And just to sort of show you, this green region here is the low pass filter, but this is the region of advective timescales is right in here. So this is the advection of these coherent eddy packets through the rotor plane, generating this part of the signal right here. All right, so now we look at the signals in these three different filtered contributions. So the black, so here I'm showing two different periods. This is over 100 seconds to 100 seconds. You always have to show these shorter seconds in order to show the high frequency content. But I'm separating it into three different groupings. The black is the total signal. All right, the green is the low pass filtered signal, which I called the trends before. So this is what I meant by trends, is we do this low pass filtering and you get this green line, which passes through the total signal in black. And then we separate out the 3P signal, which I showed you earlier, is that red filtered region. And then the high frequency, the high pass filtered signal, the high frequency content, where we've shifted this off of 0. Both of these are going through 0, but we've shifted this down arbitrarily by 1,000 just to show the different structure between them. So this is interesting. If you stare at these figures, you notice a number of useful and interesting things. One is obviously that the 3P modulations are strong. This turbulence modulation that I pointed to about the 3P, these are not uniform peak-to-peak variations. The 3P variation is clear, but the peak-to-peaks are not uniform and they're strongly modulated. There's an envelope around these 3P variations. And what's interesting is that this envelope around the 3P variations is approximately associated with the time variations of these low frequency, the trends, the low frequency content. There's a relationship between the passage of these groupings of eddies through the rotor plane and the modulation of the 3P signal. It's not perfect. I'll go into that in just a second, but it's definitely there. But what's particularly interesting is the high frequency content. So this is high frequency. It's spread out, as I showed in this previous plot here, it's spread out over a broadband range of frequencies here. But this broadband range of frequencies translates to time variations in time space that are grouped within what we call bursts of activity here. That is, there's a lot of activity and then not so much activity, then a lot of activity and not so much, and then various content and so on. Then you get more and less and so on. So these bursts of activity are important, as we will see, because they contribute to the time variations in the moment and the time variations in the force that are acting on the bearing. And it'll turn out that these are central to the largest time variations that happen on the main bearing, on the force on the main bearing itself. But for right now, just notice that these packets of activity seem to correlate in some sense with the envelope of the 3P signal, which we already pointed out is somewhat correlated to the time variations of the low frequencies. So the point is that these passages of coherent eddy structures through the rotor plane are organizing the time variation response at both the 3P, at all frequencies, at the 3P frequency, at the lower than 3P frequency, especially the lower than, you see, the low frequency content is due to the passage of these contributions, but it's then impacting the 3P and the high frequency content as well. And as we'll see, that turns out to be very important. But trying to get a little bit deeper into the relationships among these high activity regions and lower activity regions. You know, if here I'm just showing one example of where you put the high frequency next to the 3P frequency and you say, okay, here's a region of high activity and it looks like it's more or less correlating up there. And here's another time period is correlating up there. Here's another time period is correlating. So you can see visually that it appears as if there's a relationship between the modulation of the 3P by the turbulence and the generation of these high frequency, high activity, high frequency responses at the same time. And it turns out that that's true. We quantified this as best we could using various criteria. But it turns out that the overlaps between the modulations, these high frequency modulations, sort of we put envelopes on these high frequencies and we correlated them and so on. But the relationship seems to be at something like the 60%-ish type of levels, both between the low frequency content and the high frequency content, and between the 3P content and the high frequency, it's roughly at the 60%-ish or so level. So that's important, because that says that the passage of these coherent eddies through the rotor plane is creating a lot of activity on the blades, which then integrate to the forces and moments on the hub, which then gets passed through the drivetrain. And there's these periods of special activity that if there's any issues associated with these interactions, any negative contributions, like failures of the main bearing, it's going to be during these periods where the coherent eddies are passing through the rotor plane. In context with that, we noticed another interesting thing is this is just a qualitative example of something that we quantified that's in Jared's thesis that we quantified in more detail. This is the entire 1,000 second period of the, so I'm showing the total signal. This is the out of plane bending moment signal in black. The trends or the low frequency content in green, and the high frequency and the 3P frequency down here. And you can see that there's this special period in here where there's especially high levels of activity in the response in the main bearing. This would be in the main bearing as well, but on the rotor plane, the moments on the rotor plane. And it's roughly, say, between 700 seconds and something less than 1,000 seconds or so. And what you discover then is, if you ask, well, what's going on during this time period? So this is 700 seconds starting right here. And what's going on is there's this coherent low speed complex moving through at this time, right? So this is all blue in here, right? So this is a low speed time period and so on. And if you jump ahead, which I should be able to do, but it's not, all right, something happened. Well, my screen went out, but okay, I don't know what's going on. My screen is flashing. I don't know if your screen is flashing.
I can still see it perfectly.
Okay. Well, my screen was flashing, but at any rate, for some reason I can't push this forward. But when you go into a period that is, okay, now this is more red coming through. So this is high speed region coming through, and you can see this is about 900 seconds. So that the point is that period that I showed earlier. Okay, my computer is acting funny, but this period that I showed earlier is a low speed complex moving through. And that's something that we've quantified, that the coherent regions of low speed passage, low speed content passing through the rotor plane seem to stimulate these time variations with higher levels of response, higher variance levels of response than the high speed regions. That's just an interesting observation. And of course, the low speed contributions are well known as central to the high speed, to the high Reynolds number turbulent boundary layer. It's ubiquitous in all high Reynolds number turbulent boundary layers in the surface layer. And this is the point. This is where wind turbines operate. They operate, in a sense, in the most variable part of the boundary layer, and the response is correspondingly highly variable as well. So what we've learned then is that the turbulence does a number of really important things. It modulates this 3P signal a lot. It generates low frequencies, it generates high frequencies, but these regions of low and high frequency response tend to be grouped in high activity regions and lower activity regions. And if you isolate these higher activity regions, you discover that it's really the summation of the 3P response and the high frequency response, which I've shown in this picture up here. The black is the summation of the high frequency response and the 3P response. The red is just the 3P response itself. And the periods of high activity are periods where you get these large peak-to-peak variations. This is actually the bending force acting on the main bearing itself. This is the force that is causing the main bearing to change its structure. And the largest peak-to-peak variations are during these periods that I identified earlier as these low-speed passages through the rotor plane. And remember, this is happening at the minute time scale, these low-speed passages. So this is happening throughout the day, as I'll bring. These are not just one-off type things. This is normal response that the wind turbine experiences in the daytime operation of the wind turbine. So we learned that these peak-to-peaks are particularly large in magnitude as a result of the generation of the high frequency response and the modulation of the 3P response, the summation of those two. Okay, so we wanted to go into this in more detail. And so what we did is we said, okay, we'll take the signal and we'll do something. We'll just try to identify these peak-to-peak responses. So to do that, we said, okay, the peaks are when the derivatives in time are zero. So we took the derivative of the signal in time and we identified the zero crossings that's the black, the zero crossings, that's these green dots right here. And then we quantified the magnitude in the force jump during the zero crossings, and we quantified the time variations. And my computer just sort of went dead on me again. I'm sorry, you guys, I'm having computer issues here. Okay, hopefully.
But it's absolutely smooth and fine for
okay,
us.
so it's just on. All right, so just on my side, but at any rate, so I'm back again. All right, so we're quantifying these jumps and the time it takes for these jumps. So we want to know what is the characteristic magnitude of these jumps in the force acting on the main bearing, and what are the timescales associated with these. So here we're plotting this for the entire signal. So what we do is we calculate the jumps, we construct a PDF of the jumps, and then we just take the largest of those jumps. And the largest jumps we take are 2 sigma, that is 2 standard deviations or more in the PDF. So here I'm showing a plot of just the largest jumps, the 2 we call 2 sigma jumps. So these are already very large jumps. And we're plotting the magnitude of the jump and the time associated with each of those jumps. So the magnitude, and we're normalizing the magnitude on the term that is in the equation that I showed earlier that has to do with the weight of the bearing, because the weight of the rotor, because the weight of the rotor is the term that the bearing people really focus on. They don't really think too much about the turbulence, so it's all about the weight of the rotor. So the point is that when these contributions are of order the size of the weight of the rotor, so we chose 50% to mean of order. So everything above 50% is shown up here, and sometimes it's 100%. But there's a lot of dots, and this is 1,000 seconds. So there's a lot of dots up here in that 1,000 seconds. So it's really a very repetitive. It's random because it's turbulence, but it's very repetitive, constantly hitting the main bearing with these really large jumps. And the time scale for these jumps is less than a second. And there's a lot of them that are in the millisecond range, but they go all the way from 1 second down into milliseconds. So it's a very wide range of forcings on the main bearing. Here we're just trying to show that it's the high frequency content that is giving this really large range. This is the low filtered content, the band pass filtered content, and the high pass filtered content. And really this really broad range is coming from the high frequencies, and the high frequencies are coming from the blade passages through the internal structure of the velocity, the horizontal velocity over the rotor plane. And that's the nature of the turbulence wind turbine response, is these modulations and these corresponding jumps in the forces that are acting on the main bearing. So one could ask, well, okay, is this really that big of a deal? And the answer is yes, it is really that big of a deal. If you just say, okay, let's just count up all of the contributions, all of these 2 sigma. So we've already taken the largest events to begin with, and let's just count up the number of events that are at least a half of the contribution from the rotor weight, and just add them up, and you get a number like 70 or so in this 1,000-second period. So 70 in 1,000 seconds, that's less than 2 minutes. So that translates to something like 250-ish responses per hour, or 2,500 responses in a day. And of course, the wind turbine is operating day after day after day. This is in the summer, of course, but in the winter, any time of the year, this is happening. So these forcings on the main bearing are just ubiquitous. They're happening all the time, all the time, all the time. So if there's any negative consequences to these large magnitude changes in forces and direction, I should keep emphasizing that as well, there's no question that the wind turbine is going to respond negatively. The main bearing is going to fail. And we don't have proof for that, but I think the evidence is pretty strong that this is probably a mechanism underlying failure. I should also point out that, of course, these are all associated with the passage of surface layer eddies through the rotor plane. but there are turbulence eddies generated for other reasons that are interacting with wind turbines as well. And these are issues that we would like to analyze. This one's been analyzed to a certain extent in that NREL technical report. This is about mountain generated. We looked at the response of the wind turbine at the NREL site, which is next to the Rocky Mountains, in response to the mountain generated eddies coming off of the Rocky Mountains. And it's very similar to what we're showing here as the response from the turbulence eddies within the atmospheric boundary layer itself. But of course, you can also have eddies generated in the wakes of the upstream wind turbines, and there's other sources of eddies as well. So all of these need to be studied, but they're all contributing to these time variations in the moments of the hub, the force of the hub, and the force on the main bearing. All right, so what is the mechanism then? Well, I've already actually alluded to the mechanism in my discussion without really going into why we think it is that way. I've already talked about how the force in the out of plane, the torque in the out of plane bending moment are uncorrelated with each other. And I also mentioned that the torque in previous work is driven by the time changes in the rotor averaged wind speed over the rotor plane. So if this is the rotor plane, you average the horizontal velocity over the rotor plane and plot it as a function of time. Those time variations are what's generating the time variations in the torque. And that explains why the variability around the trends are lower for the torque, because that's an integrated quantity over the torque. Whereas the out of plane bending moment is actually driven by something called the asymmetry. So we define an asymmetry vector, which is representing the asymmetrical structure of the horizontal fluctuating velocity over the rotor plane. These are integrals over A, which is the rotor plane here. And it's a vector. It has a y component and a z component, where the y component is presumably stimulating the y component to the moment, and the z component is stimulating the z component to the moment. And then you take the vector and you calculate the magnitude and so on, look at the direction and so on. And it turns out that there's a really strong correlation between the time changes in the asymmetry vector, this vector itself, the magnitude and the directions, and the out of plane bending moment, which is driving the forces on the main bearing. So the conclusion is that the asymmetry in the distribution, now this is the local distribution, not just the mean, but also the fluctuations. It's the asymmetry in the distribution of the velocity over the rotor plane, how that's changing with time, that is driving the time changes in the out of plane bending moment. And it's the time changes in the rotor average velocity that are changing the torque. So there are two different mechanisms, both of which are associated with the passage of these eddies over the rotor plane. Okay, so I'm running out of time. I'm going to move a little. Okay, so no, I do have time to say this then. All right, so obviously, big question now is I think we've pretty much shown clearly that the force time changes in the force on the main bearing are, number one, being driven in these particular ways at these different frequencies by the passage of surface layer eddies, these ubiquitous low speed, high speed regions that everybody in turbulent boundary layers studies, the passage of these through the rotor plane. And I should have mentioned that the characteristic size of these eddies is the rotor plane dimension itself. That's part of the reason why the interaction is so strong, is that the characteristic dimensions are the same. And as wind turbines get larger, and as they are getting larger, they're encompassing more and more of these variabilities. So this effect is only going to get stronger. But the big question now is, do these really contribute to main? Are these the reason for main bearing failure? That's the question that is out there right now. And we're hoping to start a relationship with an industry to answer that question. It's not a trivial question. We have to model the main bearing, and at the same level of fidelity that we're modeling the velocity field and the wind turbine itself. So we think the answer to the question is yes, but we haven't proved it. All right, so this is the summary, that the time changes in the bearing force are largely driven by the time changes in the non-torque moment, the out of plane or radial moment vector that's acting at the hub of the rotor, which is integration over the three blades in time. And that the time changes in these out of plane bending moments are driven by the interaction between the rotor blades and the gradients over the rotor disc, both in the mean and the local gradients. As these blades pass through these high gradient regions, they generate a time response, and that's at the high frequencies. The atmospheric turbulence has a dramatic impact on the 3P. This is really important, I think. The 3P is well known. I mean, everybody knows about the 3P fluctuations, but the turbulence impacts on 3P are dramatic. They really change the magnitude of the 3P, and they change the structure of the 3P response. And that's really important for the drivetrain. And the atmospheric turbulence generates these modulations within the 3P range and the lower frequencies and at higher frequencies than the 3P range. And it's the integration of those three frequencies that are generating the largest time variations in the main bearing force itself. And these are all attached to the surface layer eddy structure, which takes us to the fundamental turbulence of turbulent boundary layers. Now, there's a number of other studies that we've done. I don't have time to go into, but we have also, I didn't mention that the blades are rigid in this calculation, constant RPM. We've done an analysis of deforming blades, you get the same results. And we have not included controls, and that's important. We need to include controls. We've also compared the impacts of real turbulence versus kinematic turbulence, including the Kymel model and Jakob's Mann model as well. And that's something that I know Jakob would be interested in. I'll talk to him about that at some other point. But there are major differences. The kinematic turbulence doesn't capture these high frequencies correctly, or let's say it doesn't capture them in a way that predicts these large responses in time on the main bearing. All right, thank you very much. That's it.
Thank you very much, Jim. Very interesting, and we have time for a few questions. So either you just speak up, I think that's the easiest, or you can also use the chat. So I can start. So you have this asymmetry measures, and then you make the length of this asymmetry vector, and that's uncorrelated with the rotor average horizontal wind speed. But are each of the components, I guess they are also uncorrelated to
Yeah, they are. We've analyzed the components. Obviously, in this talk, if I went into those details, I wouldn't have time. But no. Let's see. Yes, we've analyzed all those details. So that's this slide right here. And these components are correlated with the corresponding components in the moment, and they're uncorrelated with each other. And this is partly a kinematic effect and partly a dynamic effect. That is interesting. It's probably kind of getting down into the weeds about the physics, but yeah, there's some interesting relationships there.
Another question is, I would think control had really a big impact on all this. Well, what are your thoughts about that?
Oh, I agree. I think control will have a big impact. Since these time variations are everything I'm showing here is totally driven by the turbulence. And obviously, so let's do the deforming blades. So one of the issues with deforming blades is it's responding to the turbulence as well. So you've got a whole new dynamical system that's responding to the turbulence as well. It's the same with controls. Well, we found out that the blade response is generally at the lower frequencies and don't really contribute to these high frequency responses that I was showing are the result of this result here. But the controls obviously are going to be there in order to maintain constant RPM, for example. We assume constant RPM, and there's controls, braking and so on. And I'm sure that it's going to have a strong influence on, it'll probably generate new frequency responses, and those new frequency responses could be detrimental as well, and it'll probably modify the frequency responses that we're already seeing. So I think controls have the potential of making the situation worse, but we shall see. We need to do controls. You're right. We haven't done it with controls.
Good. Any other questions?
Yeah, well, I have a question. So you mentioned, thanks for your presentation, Jim. You mentioned some potential future studies look into mountain created turbulence and also wakes. Did you also consider the possible effect of convective rolls?
Well, the convective rolls are in our simulation. They're at the very large scales. They're actually at scales larger than I actually showed in the frequency content. So I don't think they're going to have. I mean, they'll modulate at a very large time scale, but I don't think they're going to have any impact on the stuff that I'm talking about here regarding the main bearing impacts. Yeah.
Okay.
But with regard to what you were saying about the mountains, so if you're interested, if anybody's interested, there's a technical report that we wrote, and I can send that to you. Just send me an email. But it is about we were actually, since the NREL site, if you're familiar with where the NREL site is south of Boulder, it's right next to the mountains, and it's experiencing the response to the mountain eddies that are coming off of the mountains. And we analyzed those correlations that I alluded to earlier, and you get exactly the same correlations from the mountain eddies. And we analyze them, and we show that the energy content is similar to the atmospheric boundary layer eddies and so on. So I think those mountain eddies are providing very similar kinds of responses. But of course, there's various kinds of mountain eddies as well. So, I mean, yeah, all of these things are going to contribute to the frequency content and to the magnitudes of the responses. Well,
but what about wakes in combination with convective rollers? So you have a wake membrane, and you can imagine that this dynamics could be increased by convective rollers.
Yeah. Well, okay. So let me just say about the wakes. I think the wakes are going to be important, especially when you've got wake steering going on. It's going to definitely contribute frequency content to the responses. In addition, and I would argue that the wake meandering, the reasons why the wake meanders as much as it does is really because it's interacting with these energy containing motions, these so-called low speed and high speed streak regions. That's the main reason why. So I think it's probably going to add into the low frequency responses. But as the wakes pass over the downstream rotor, it's going to generate, as the blades cut through that eddying structure, it's going to generate new frequency content that I'm sure is going to be very important in addition to what we're showing here. Yeah, but we haven't looked at it. If anybody would like to provide us some funding to hire a postdoc to answer that question, I'd love to receive the money.
Okay, it's we are at time. I'd like to thank Jim very much for a really fascinating presentation. Great work, Jim. This series is going to be on hiatus for the summer, and we'll see what happens afterwards.
Okay.
And yes, the recording will be posted on the NCAR website probably later this week.
Great. All right. And if anybody would like to discuss, send me an email.
Okay. Thank you very much, Jim.
All right. See you.
See you.
Thank you.